Hello, I guess it's working, or if it doesn't work, okay. Let's discuss now the phase equilibrium in one component system. In any thermodynamic conditions or any equilibrium condition is determined by its pressure, temperature, and composition of the system. So this is actually the equation is given by Clausius and Clapyeron, two scientists, and is named after them. So this equation gives the equilibrium state given by a given set of temperature and pressure. So temperature and pressure determine the state of equilibrium of a system. I guess it's working fine. Sound is okay. Yeah. So for any equilibrium condition, please note that the pressure and temperature is very key important. So just go back to this slide. Look at this plot. Right, in this y-axis there is a vapor pressure, and at the x-axis there is temperature. So along this line, for ethyl alcohol, diethyl ether, and water, there is a certain combination of pressure and temperature. For example, along this line, water is in equilibrium with steam. Okay, steam is the condensed phase, so it has a vapor pressure. Water is the liquid phase, this condensed phase. So for each of this, this lines determine the state of equilibrium. That is, the free energy change is zero. What is the free energy change? There is a free energy change from for a phase change. So there is no free energy change. So water won't convert into steam, steam won't convert into water. There is no mole change. Number of moles of water and steam will be kept constant for a given equilibrium state. So please remember this. These lines, so equilibrium always means that there is no mole change. Given amount of solid is in equilibrium with given amount of liquid, or given amount of vapor. That is what is called equilibrium. So if you change the pressure, the equilibrium will be disturbed. So you have to correspondingly change the temperature to make the free energy zero. I'll just explain it with one of the diagram when I start discussing it in details. So please, this is what we talk about. This is the equation is about. Okay. So if we'll just come back to the earlier slide, there's a relationship between the temperature and the pressure for an equilibrium, which is given by Clausius-Clapeyron Equation for a given number of moles of a particular material. And this pressure and temperature is related to the enthalpy change, the universal gas constant, and etc. Okay. So now get back to the slides that we are talking about. Okay. So now we will talk about how to determine equilibrium, what it is all about. Okay, fine. Okay, let's see. So our topic is phase equilibrium in one component system. We are talking about only one component. That is the same material, right? There is no multiple components. There is water and ice, ice and vapor. This is a one component system. So what we talk about, first I will start with the concept of a free energy. Again I will revisit the concept of free energy. Let's see what it is. So talked about G is equal to H minus Ts, right? H minus Ts. So this is a thermodynamic quantity which is defined by H minus Ts. These are functions. G is the free energy of a system, H is the enthalpy of a system, T is the temperature, and S is the entropy of the system. So I need to find the dG. Why? Because dG gives me the change in free energy. As I already talked about, delta G is less than 0. It's a spontaneous process. For, let's say, for A to B, its delta G is less than 0, A will convert to B spontaneously. Delta G is 0. This is what we are talking about. A is in equilibrium with B. Okay. A is in equilibrium. This is the equilibrium condition. Equilibrium condition. So A won't convert to B, B won't convert to A. Okay? So the composition remains constant. Number of moles of A and number of moles of B remains constant. Here, the number of moles of A will decrease and number of moles of B will increase. And delta G greater than 0. That means A will not convert to B, B will convert to A. So this backward process is spontaneous. For the forward process, delta G is less than 0, A won't convert to B. Okay? So these are the three conditions that may occur. So for any equilibrium condition, may it a chemical reaction or may it is a phase change. So I have already talked about there is two kind of equilibrium we talk about. One is the reaction, R1 plus R2 converts to R2 plus R3, R3 plus R4. Okay, these are the reactions that we talk about. Another is the phase equilibrium. There is no change in temperature. There is no change in the there is no change in the compositions. There is a fixed composition, fixed component. It's a liquid, or let's say alpha beta equilibrium. Okay, if M is a material which exists in three states, alpha, beta, gamma, it can have multiple states. Okay, for a given temperature. So we talk about equilibrium for the same material, equilibrium between alpha, beta, and gamma. So this is commonly called as a phase equilibrium. Okay, right? Fine. I guess there was a change, a fluctuation in my power system. Anyway. Okay, fine. So now we'll discuss how to approach a problem, how to find this dg. Dg gives me the equilibrium condition. Okay, so whenever we talk about equilibrium from now onwards, we'll think in terms of change in free energy of the system. Change in free energy of the system will give me whether the process will occur, the system is in equilibrium or not. Fine. Right? Let's see how will we give it. dg is d of h minus ds, which is dh minus dds minus s dt. Right? I have taken just the differential. Right? H is u plus pv. Please refer my earlier lectures. We'll find these relations. I have talked about this in multiple times. So dH is du plus pdv plus vdp. Right? Now du. What is du? From second law of thermodynamics, it is S TdS minus pdv. This is a combined statement of first and second law. Okay, du is TdS minus pdv. So if I substitute this ds here in the du term, so pdv will cancel out. Okay, so TdS plus vdp. Here there is a minus TdS. So if I substitute dH here, this TdS will cancel out. So what you are left with vdp minus sdt. Okay. vdp minus sdt. So your final expressions becomes dg is, you can pause the video and note it down if you have any doubt. vdp minus sdt. Right? So this is the dg. Okay, fine. So now if this is the condition, if this is the condition, this is the change in free energy for, so let's say for liquid, I am talking about liquid, the equilibrium between liquid and solid. Liquid and solid. So let's say for liquid, what it will be? This is V liquid dP minus S liquid dt, right? And for a solid, V solid dP minus S solid dt, right? So this will be the equilibrium. We can talk about alpha, beta, liquid, anything. Okay. So for an equilibrium condition, if I say that the liquid won't convert to solid, solid will not convert to liquid, the moles will be constant. So the free energy change will be zero. That is delta G is zero. That is GS minus GL is zero, right? Free energy, or in any case, we can then change that the change in free energy is also zero. If no GS and GL are zero, the change in free energy is also zero. So if this is the state, or this is the thing, so we can write that dGs is equal to dGl, right? So if I just equate this to change in free energy for both of the system. So VLdP minus SLdt is equal to VSdP minus SSdt, right? At this point of time, I just want to draw one graph. Please note it. This is the G, this is temperature, constant. This is pressure, let's say this is pressure. Let's say pressure at constant temperature. Let's say 0 degrees centigrade. This is 1 atmosphere. Okay. So look at here. I always talked about one thing, that is the free energy of the final state will be always lesser than the free energy of the initial state. So that always gives me one thing, that is the free energy change is zero. So liquid must have lower free energy than solid, okay, below the freezing point. Sorry, above the freezing point, right? So below the freezing point, the solid must have, the solid must have lower free energy than the liquid. That's why the solid is stable. Okay. So this line is solid, okay, and this line is liquid. So let's say this is the freezing point. Okay, let's not define it this way. Here you have only temperature is constant, so let's say don't define it this way. Because my temperature is constant. So let's define it in this way. Whatever happens, my free energy of the final state is lesser than the free energy of the initial state. So let's say this is liquid and this is the solid line. Okay. This is at 0 degrees centigrade. Okay. At 0 degrees centigrade, this is 1 atmosphere. Let's say this pressure is 1 atmosphere. Now look at this. If you increase the pressure is the variable. Either you will lie at a liquid line. Sorry, this is liquid, so this is liquid. This is solid. This is solid. Okay. So, if you increase if you increase the pressure, okay, beyond here, you have solid or liquid. If you increase the pressure beyond this, you will have a liquid. Why? Because your free energy is lesser than the solid. So at a constant temperature, if you increase the pressure of a system for for a particular phase, now I'm going to talk about always the solid liquid will depend on whether there is a volume change, is negative or positive. We'll talk about that later. But for this system, if you increase the pressure, the liquid seems to have lower energy than the solid. Therefore, liquid is stable. Beyond this, this is the equilibrium point. This is what we talk about. See here, the liquid and the solid has same free energy because they are intersecting. They are the intersection point. The liquid has the same intersection point as with the solid. So free energy change is zero. The GL is same as GS. So this is the equilibrium point for a given pressure and temperature. For a water, for H2O, this is 1 atmosphere and 0 degree centigrade here. Okay. So this is the, so please understand, this is GH2O as a function of pressure. We have plotted. We'll get a plot like this. For liquid, for water, this line will follow like this, and for solid, this one. This is ice. Beyond this point, if you increase the pressure, liquid seems to have lower free energy, so you will have always liquid in the system. If you decrease the pressure, the solid seems to have lower free energy, so it will be a solid. Okay. So remember, this is occurring at a constant temperature. You cannot have three variables at the same time at a two-dimensional plot, right? So there are only two variables, free energy as a function of pressure. So if you increase the pressure, now the important concept, if you increase the pressure, you lie somewhere here, let's say here. So what happens? Your solid in the system transforms to liquid. Okay? Your solid transforms to liquid. Because liquid has lower free energy than the solid. Beyond this point. So solid transforms to liquid. So there is no equilibrium. Your solid is continuously being transformed into liquid. Now say, I want to establish the equilibrium at this particular pressure. Let's say it's P1. Again, what is equilibrium? The conversion will stop. Water to liquid, solid to liquid, conversion will stop. So that means that I have to play with this temperature. I cannot keep it zero and increase the pressure to have an equilibrium. So I have to adjust this temperature in such a way that there is a new equilibrium at this given temperature and pressure. Right? So that my free energy is again zero. Do you understand now? So that the relationship between pressure and temperature, okay, to establish an equilibrium is exactly the Clausius-Clapeyron equation. That is what it talks about. It talks about a pressure, combination of pressure and temperature to establish an equilibrium for a particular state. Or if I change the pressure, what is the change in temperature to re-establish the equilibrium? Or if I change the temperature for a G versus temperature, what will be the pressure to re-establish the equilibrium? Otherwise, if you just keep one temperature constant, change the pressure, the system moves from equilibrium to non-equilibrium state. That means there is a spontaneous conversion or transformation of phases. Fine. Now let's say I will just stop with this one. A lot of questions are asked from this. That's why I talked about this. Okay, so now let's see. This dp/dt is what we are talking about. Change of pressure with respect to temperature. So I have to have this term, right? Sorry, my marker is not working, I guess. This is what I'm talking about. I need to know the change in pressure with respect to temperature, and I have to establish this change with respect to some measurable quantity, or for calculation's sake, let's say from free energy, let's say enthalpy, temperature. Anyway, I have to have an expression for dp/dt. So if I just want to do this, so what it will be, look at here. So dp is, if I talk about dp dt, it is at equilibrium. You can also do that. Okay, minus S liquid dp, let's say dp here. So I will have here S entropy of solid minus entropy of liquid divided by, okay, pressure term is here. Just check if everything is right. Also, so let's break it up. It will be better that I will break it up. Okay, so dp vs minus vl is dt, comes here ss minus sl, right? So dp dt is what? Entropy of solid minus entropy of liquid divided by volume of solid by volume of liquid. Understand this? So this is the most important equation, or we write it as dp dt is equal to del S by del V. Solid minus liquid by delta V, solid minus liquid. Okay, or we'll say solid minus liquid, solid minus liquid. Just, you know, I'll just write it clearly over here. This is the very, very important equation. Please note it down. Lot of questions are asked. dt dp for equilibrium is delta S liquid to solid divided by delta V liquid to solid. Please note that this delta S must be maybe positive, maybe negative. This delta V may be positive, maybe negative. So please be very careful with the, you know, final volume minus initial volume, final state minus initial state, that is entropy of solid minus entropy of liquid, and volume of the solid minus volume of the liquid. So normally volume of the liquid is, you know, larger than the volume of the solid. So normally it comes, you know, a negative sign comes. But this is the anomalous with the water. You know, when, you know, water converts to ice, the volume increases. That is normally not the case with any material. Normally liquid has a higher volume. So entropy is positive. We'll talk about its, you know, implications. So this is the very, very important equation. dp dt at equilibrium is delta S liquid minus delta solid by delta V liquid minus delta V solid. Okay. So now from this we'll go a fewer assumption. Now we'll talk about delta G. Okay. So let's see what happens at equilibrium. So delta G is 0. I guess it's not visible. Right in this. So delta G equilibrium is 0. At equilibrium there is no change in free energy, right? So delta G del H minus T del S, right? So, you know, entropy change. So why don't we keep it at this form? This is the basic question you should always ask whenever we go for any derivation. Why don't you keep it in this form and change a calculate? See here, look at this expression. can you measure entropy? If I want to ask you, just measure entropy, you won't be able to measure entropy. So entropy has to be substituted. You know, I talked about pressure, volume and temperature, those three terms, or you know, heat, Q or W. These are the terms that you can, this is the quantity you can measure. So I cannot keep it in this form because it is not convenient for me. Otherwise there is no problem with this, you know, entropy change. I always want to think in terms of delta H. There is an advantage of delta H. Do you remember? At constant pressure, del U del T is Cp and is also del H del T. If you remember, I have written this expression. So enthalpy and everything, those have disadvantages. So now talk about in terms of enthalpy. So enthalpy is a measurable thing, right? The change in internal energy or the change in, you know, del Q del T at constant pressure is del H del T at constant pressure is Cp. So the heat energy change in the system with respect to temperature can be given by enthalpy. So enthalpy change basically is the heat evolves or it given at a constant pressure. So I can deal with this, you know, enthalpy change or the concept of enthalpy. So I will just, you know, write in terms of enthalpy. Let's see. So this becomes 0. So my idea is to replace entropy with enthalpy. So delta S becomes del H by T. So if I write this, this becomes delta H by T delta V. Right? So this is just another form of expression. Now, let's see. Now think about this V. See, sometimes you will be asked question. Please note it down. It's another equation 2. This is also very important. Sometimes you are given the enthalpy, the volume change between two states and the temperature at which the temperature must be changed. So normally we express this dP is equal to delta H by T delta V dt. This is the expression. You have to do an integration P1 to P2. So what does this mean? If pressure is changed from P1 to P2, the temperature has to be changed from T1 to T2 to re-establish the equilibrium. At a different pressure, you have a different temperature to establish the equilibrium. That's what it gives. Normally, if enthalpy and, you know, del H by P, del H by V is not a function of temperature, then you can take it out. You can write delta H by delta V ln T plus constant. If there is no temperature, I've kept this, you know, integration constant. It's not a definite integral. If it is an indefinite integral, so this constant comes. For a definite integral, you have ln T2 by T1. So these are all, you know, substitute equation from this main equation. Everything is coming from here. Okay. Now let's see for a condensed phase and vapor phase. So please note these equations down. So this is the expression you should, you know, remember. So now this is the important part, the equilibrium between condensed phase and vapor phase. Equilibrium between condensed and vapor phase. So what we have talked about, we have seen that dP dt, equilibrium, is given by delta H by T delta V, right? Delta V. So for a condensed phase, the equilibrium between a condensed phase and a vapor phase, this P is the vapor pressure of the system, on the system, right? Vapor pressure. So what I mean about, so if it is the condensed phase and this is the vapor phase, so let's say water and let's say water vapor. So the vapor exerts a pressure on the water at a particular temperature, and let's say there is no spontaneous condensation from water to vapor. So in this case, the pressure is actually vapor pressure, saturated vapor pressure. It doesn't change, it remains constant. So for a saturated vapor pressure of a material, it obeys the Charles and Boyle's law, that is the PV equal to RT, right? So we'll substitute. So PV equal to RT, right? Now what about this delta V? Delta V is what I have said. You remember? Just go back to the just get back to the session where I talked about delta V. The delta V is, the solid V solid minus V liquid is your delta V. Just go back and please ensure that this is this way. Okay, solid minus liquid. So for a condensed and vapor phase, this solid, I won't say solid, let's say it's a vapor pressure, it's a liquid to vapor, VV liquid. This VV is much higher than the, so V vapor, the volume of the vapor is much more than the volume of the liquid. So delta V can be written as vapor. These are important substitution. You should know this. It's not that you just apply according to your wishes. I won't write it here liquid. I will just write condensed phase. So volume of the vapor is much higher than the condensed phase. So delta V is V vapor minus D condensed phase, which can be substituted as only vapor. So if it is only vapor, so how do I replace this? V vapor is RT by P, right? So if I just write it here, what it becomes, dP dt is equal to delta H by, delta V, RT by P goes to the top, so P by RT square. Okay, P by RT square. So if I let's write it. So dP by P is delta H by RT square dt. This is another form of Clausius-Clapeyron. It's actually called the Clausius-Clapeyron equation. See, here everything is known. The enthalpy of the system you know, and this is the universal gas constant. So just knowing the enthalpy of the system for a particular set of conditions, you can actually determine the any pressure and temperature combination to establish the equilibrium. So normally if I integrate it, I will just do dln P. So let's do it. Integration P1 to P2. dP by P is integration del H by R. I will just keep it outside. If it is, remember, H is not a function of temperature. If it is not a function of temperature, keep it out. Depends on your problem by T square. So T1 to T2. If I just move this to definite integrals, so I will have ln P is minus delta H by RT plus constant. This is the final form, another form of Clausius-Clapeyron equation. Then ln P is delta H by RT plus constant. This is very important. I will solve a lot of problems with this concept. Okay. So ln P is delta H by RT plus constant. So equilibrium change in temperature and pressure will be expressed, or for a given, if I am given with an enthalpy change for a particular temperature, at that particular equilibrium, if I know the enthalpy change, so I can establish equilibrium at any pressure with a change in temperature. Or if I change the temperature, I have to change the pressure accordingly to establish the equilibrium to make it delta G is equal to 0. Otherwise, your free energy will either be positive or negative. So it is a deviation from equilibrium. This condition gives you ln P del H by RT plus constant, the combination of pressure and temperature to establish an equilibrium to make delta G 0. Clear? Pressure and temperature relationship. How pressure and temperature varies to establish an equilibrium. That is what it gives. Okay? Done. Fine. And let's solve some problems to understand how to tackle this, enthalpy. And sometimes, this delta H will be given in terms of, and always remember this H is also, sometimes what happens, this enthalpy or this enthalpy change, this delta H is also Cp dt. Okay. So sometimes you have to take care of that. So we'll see how this entropy will be, enthalpy will be calculated. Okay, fine.